He did his bachelor degree in physics at Oxford, and then he did his PhD at Boston University, and then he did something in India, right, Ranji? You did something related to schools. I just had hard time understanding.
Yes, a long time ago.
Long time ago, and then he's now a full professor of physics at the Universidade Federal do Rio Norte, where Daniel Takahashi is also in Natal. Too bad we could not have you in person, but thank you for agreeing to talk. And yeah, we will have mics for questions. So if people have questions, please just ask for the mic. Randy have a long-standing interest in foraging, and I just realized that I have his book, Physics of Foraging, for some time now, and I just looking at the name, I realized that the same talking today. Thank you, Randy, and the floor is yours.
Okay, thank you very much. So I hope
yeah, we can
you
hear
can
you.
all hear me, that the volume is good, that
Yes,
the sound level
yes,
is
we
good.
can hear you, and we can see the screen.
So good morning to everybody. And before I begin, I would like to thank Ahmed El Hadi and Daniel Yasumasa and the other organizers for inviting me to speak here today. And I apologize that I am not there in person. Circumstances did not permit this. So the title of my talk is Lévy Walks on Search Optimization, Free Will, Randomness, and Determinism in Animal Locomotion. I sort of made my career studying Lévy walks. And these concepts such as free will and determinism, randomness, they end up being part of this topic of Lévy walks. And I would like to present some of these ideas here at the school on the origins of life, behavior, and cognition. So I'm going to build my talk around the main problem which I have been studying for many years, which is the Lévy flight foraging hypothesis, and I will present some technical results on search models and with some discussion and conclusion, but I would like to place it in this larger context of determinism, random walks, and free will. These are some of my collaborators. Ernesto Raposo is now a professor in Recife. Marcos da Luz is a professor in Curitiba. Ernesto and Marcos are my longtime collaborators for many years. Gene Stanley is now retired. He was my PhD advisor. Sergei Buldarev is also now retired. He was a professor at Yeshiva University in New York. Shlomo Havlin was the president of the Israeli Physics Society and has been collaborating with me since my PhD days. Marina Wozniak was a PhD student of Marcos da Luz and is now in Europe. And Federico Bartomeus is the biologist, the ecologist with whom I have been working the most over many years. So the main technical problem we study is the question of what is the optimal way to forage? What is the optimal way to search for randomly located targets? And we thought we had more or less given a reasonable answer for this question. My collaborators and I felt we had given a reasonable answer to this question maybe 10, 15 years ago, and many of us actually started working on other problems. But recently, around the time of the pandemic, the question about the optimality of Lévy walks became newly controversial due to a paper published in a top physics journal. So once again, several of us got together and decided to take a new look at this problem. So I will be presenting some of these technical results. I will explain the controversy and show you what is the current understanding, what is the state of the art in this field. Now, why is this an interesting problem? Well, the whole concept of searching for targets is very important in biology because extremely important processes such as eating. Oh, sorry. Center speaking while I'm joking. Sorry. Extremely important concepts such as eating and mating are search processes. Many animals must search for food, and similarly, males and females must somehow find a mechanism to find each other in order to mate. There are also technological applications, for example, searching databases, searching the internet, and so forth. There's also an abundance of experimental data. There's now a huge collection of empirical data that can be analyzed, consisting of millions of data points. And so it is possible to test various kinds of hypotheses of how the animals move and so forth. Now, there's also a very interesting interplay in the search problem between what we might call free will on the one hand and physical and biological constraints on the other hand. So, in principle, animals can choose how they move. I mean, they can go left or right, and this decision is made endogenously by the nervous system of the animal in one sense. But on the other hand, there are physical and biological constraints. For example, an animal cannot go without food for too long, because if it doesn't get food, it may die. And so there are these constraints that kind of delimit how much of this so-called free will is allowed to play a role. On the other hand, these constraints are not fully deterministic. There is the famous traveling salesman problem, which is another kind of optimization problem where you have a salesman and he or she has to visit a number of cities, and there are traveling costs from city to city, and each city must be visited exactly once. And then the problem is, what is the order of the correct, what is the correct order to visit each city so that the costs are minimized? If you have n cities, you have n factorial permutations. And so this is a very difficult problem computational. It's what they call NP complete type of problem. But in biology, we don't have this kind of problem because many times you don't know what the costs are. There are some uncertainties. And so it is not fully deterministic, but it's also not fully random. And so you're exactly in between these two regimes of fully deterministic behavior and fully random behavior. Now, free will necessarily lies somewhere in between these two regimes, or perhaps it involves a mix of these two kinds of dynamics. Before the era of quantum mechanics and before the discovery of chaos theory, there was a big question of whether free will was possible in a deterministic world. Some schools of philosophy, the school is called compatibilism. They believed that it was possible to have free will even in a deterministic universe. I myself I can't understand or accept this way of thinking, but there have been attempts to think that to rescue free will in a deterministic universe. Now that we know that the universe is not deterministic because there is an intrinsic probabilistic aspect to quantum mechanics, even the very smallest uncertainties can also be amplified due to the butterfly effect in chaos theory. There's more space for what we might call free will. Nevertheless, I would say that the majority of people working in biology and neuroscience are sort of skeptical that free will is really free in some sense. A more operational way of thinking of free will is as self-initiated action. So if you have an organism or an animal and its nervous system endogenously makes some decision to go, say, left or right, this self-initiated action can be seen as a sort of proto-free will. And this has guided a lot of the research. Nevertheless, it's worthwhile to point out that free will also, the way we think of free will in society and in cognitive science and so forth, often involves some aspect of consciousness, which I won't be discussing, but I think it's worthwhile to point out this aspect of free will. So here I give an example of a very, very famous legal case in Canada. I think it went to the Supreme Court of Canada. So this young man, Kenneth Parks, I think he was in his 20s, and he had a disease, this condition of somnambulance, so sleepwalking. He has chronic sleepwalking, and he needed to take medication. But one day he didn't take the medication, and so he got up in the middle of the night and moved around. Now it's actually very interesting, the connection with Lévy walks, because I will show what a Lévy walk or a Lévy flight is in a little bit. I will show graphs of Lévy walks. But different from Brownian motion, where the step sizes are the same, in a Lévy walk or in a Lévy flight, there will be many small steps and then one or two giant steps that take the random walker very far from where he was diffusing previously. And so Kenneth Parks started moving around in his house and then got into a car, drove 20 kilometers. This is the giant leap, the giant step typical of Lévy walks. And there he, using a key that his mother-in-law had given him, he entered the house of his parents-in-law and committed a homicide. And soon after, he woke up and he went straight to the police station and he said, I think I did something very bad because I woke up with blood on my hands. And so this homicide case went to the courts, and it was very interesting from the legal point of view, because could he be guilty if he was not conscious? Because he was actually asleep and he had no memory of what he did when he was sleepwalking. Finally, he was acquitted of homicide, and the court went all the way up to the Supreme Court, and the courts maintained that since he was sleepwalking, he could not be guilty for the homicide that was committed. So this example shows how complicated these aspects of free will that I will not be able to discuss in this talk. Also notice that free will cannot just be self-initiated action, because clearly this young man, his actions were self-initiated. Although he was not conscious, although he was asleep, there's no question that it was his brain that did the self-initiated action that led to him going 20 kilometers away and take this tragic homicidal action, and then drive to somewhere else, to the police station. Okay, so let me continue. Okay, so going back to the technical aspect of this talk and Lévy walks, it used to be in the 1970s and the 1980s that the diffusion of all biological organisms was thought to be governed by Brownian motion and by the theory of normal diffusion. So this is the diffusion governed by the classical Fokker-Planck equations, the classical Langevin equations, the classical master equation, and so forth. The very first time it was conjectured that maybe more exotic types of random walks might play a role in biology was in a 1985 conference in Cargès. And from what I hear, the conjecture was actually originally posed somewhat in jest, whether maybe a Lévy walk could be used to search for one of the conference participants who had gone windsurfing and people were looking for him, and someone suggested maybe a Lévy walk might be able to help search and find the missing participant. After this, this idea was eventually found its way to this paper by Mike Schlesinger and Yossi Klafter, published in this book in 1986. And soon afterwards, a number of papers started looking at these exotic kinds of random walks, such as Lévy walks and flights. And it was also in the 1990s that I myself started becoming interested in this problem when I was still a student. So let me give you some of the basic science and mathematics as to why it took a reasonably long time for more exotic kinds of random walks to be considered in the biological context. So if we look at random walks, such as the Brownian random walk, usually the step size distribution has a finite variance. And that, for example, if you just take the famous drunkard's walk, where you throw a coin many times, and if it's heads or tails, you go left or right. This kind of step size distribution is just a simple bimodal distribution. You either have +1 or -1. But in general, you can have a different distribution. But if the step size distribution has a finite variance, then we know from the central limit theorem that the sum of independent and identically distributed random variance with a finite variance necessarily converges to the Gaussian distribution, the normal distribution. And this is why you get Brownian motion, and the theory of Brownian motion is called normal diffusion in the context of transport phenomena in physics. Now, usually the case of infinite variance is not considered. It was Paul Lévy in the 1930s who first considered the case of infinite variance. And this isn't so unrealistic as people may think. For example, the famous Cauchy distribution, or sometimes also known as the Lorentzian distribution, has an infinite variance, an infinite standard deviation, which is why for the Cauchy, the Lorentzian distributions, the way to measure the width of the peak is using, for example, the full width at half maximum or the half width at half maximum, and so forth, because you can't use the standard deviation because it is infinite. Now, when the variance is infinite, the central limit theorem is not applicable, and then you have to use the generalized central limit theorem. And the stable distribution is no longer the Gaussian distribution, but the Lévy distribution. So let me define some terms here. I will give a somewhat simplistic definition of these terms because there are borderline cases and so forth. But in general, if the mean squared displacement grows linearly in the number of time steps, then we say that the diffusion is normal. And this is what happens, for example, in the drunkard's walk and in Brownian motion, the mean square displacement grows linearly in time. And of course, the shape of the position distribution is a Gaussian. Now, if this is not the case, then we say the diffusion is anomalous. For example, if the diffusion grows not linearly in the number of time steps, but proportionally to some other power of the time, then we say the diffusion is anomalous. So we can ask, when should we expect Brownian motion and when should we not expect Brownian motion in the context of biology? The answer is usually we can expect Brownian motion, since that's the more common situation. But there are certain situations when you might have, for example, an infinite variance. For example, imagine an animal that the step lengths are given by the Cauchy or Lorentzian distribution, like I said, then you will have Lévy flights. Another situation is where the step lengths are small, so you have a finite variance, but there is memory. There's memory correlations. For example, imagine again the situation of the drunkard's walk, where you throw the coin many times. It's heads or tails, so you go left or right. But now imagine that instead of having a random coin, you have some kind of magical coin, and every now and then you will get 1,000 heads consecutively, or 1,000 tails consecutively. So you will go to the left 1,000 times, or you will go to the right 1,000 times. And there are these correlations. So these kinds of correlations can also cause anomalous diffusion. In both cases, what we need is some kind of power law in time or power law in space. Power laws are scale-free. They have a scale-free property, and this is why this anomalous behavior happens. And it's important that these power laws, they extend to the size of the system or to the duration of the measurement time period. On the other hand, we should expect normal diffusion if the central limit theorem is applicable. So in the literature of the 1980s and early 90s, it was believed that these exotic behaviors could be caused, for example, by long-range memory effects. For example, maybe an animal will learn something about its environment, and this memory will make the animal behave with long-range order. Another possibility is that the environment was long-range correlated. For example, a fractal environment. And these two possibilities were the main motivations for studying exotic random walks, such as Lévy walks in biology in the early 90s. And then my collaborators and I, towards the end of the 1990s, we proposed a different idea, which became known as the Lévy flight foraging hypothesis, which I will show you some of these results. And the basic idea is that Lévy walks and Lévy flights are actually help to optimize search efficiency under certain circumstances, and therefore natural selection, Darwinian natural selection, would have led to innate biological mechanisms, so neurophysiological mechanisms inside organisms to generate Lévy walk and Lévy flight type of behavior. And this would be another reason why you might find exotic movement in the behavior of animals. So let me show you some figures here. I will show more figures in a few slides later. So this first slide, let me see. I think it's, I hope you can see the top slide, but it's a Cauchy distribution and a Gaussian distribution. The Gaussian,
Randy,
the
sorry.
dashed line.
Sorry to
Yes.
interrupt you, Randy. Can you just remove, because this panel is on your side, not on our side, and the screen up.
Oh, this thing?
Yeah, if you can remove it just more. Yeah, exactly. Where is the, yeah.
No, I did something wrong. Oh, one moment. Huh. I don't know how to get rid of this.
Okay.
Maybe what I can is, let me try doing this. Just for this slide, I will show it like this.
Okay, so can you just take it a bit down? Yeah, so that we can,
Yes.
yeah, that's it. Yeah, we can see it, it's fine.
Yeah, so I will go back to the other mode of presentation as soon as I finish this slide. So this top graph, maybe I can even make it bigger. So this top panel shows a Cauchy and the Gaussian. They look very similar. The dashed line is the Gaussian. But if you look at it on a semi-log plot, so now the vertical axis is in a log scale, you can see that the Gaussian is a parabola. It's an inverted parabola, but the Cauchy distribution is not a parabola, it has a fat tail. If you look at the distribution on a log scale, then the Gaussian has a very, very rapid decay, but the Cauchy has a power law decay, a straight line on the log plot. So this is the signature of power laws, is a straight line on the log plot. Perhaps the most famous is the Gutenberg-Richter law for earthquakes. Okay, so, oh, one moment, let me see, something wrong here. Okay, so I will now give you some biological results, tell you the story. So in the 1990s, there were the GPS technology for tracking animals was not yet developed. And it was during these pre-GPS days that I got involved in this field. And because the equipment in those days was bulky, it was not possible to easily study the movement of, for example, small birds. However, the wandering albatross is a very big bird. It has a wingspan of several meters. An adult can have a wingspan of more than 3 meters. And so it can easily carry a small radio transmitter. And so these were the animals that were used in some of the first studies of my collaborators and myself. The male birds can weigh more than 10 kilos. The females are a little bit smaller. They're incredible animals from the point of view of how much they can move. They can easily travel 500 kilometers in one day. Their diet is small fish and squid. And in fact, they have, like humans, sometimes they eat too much. And when they eat too much, they have difficulty taking off because they will be lying on the water, sitting on the water. But sometimes they eat so much that they don't get enough lift to take off. So they have to wait to digest the food before they are able to take off. In in the very low southern latitudes near Antarctica, they regularly circumambulate the whole Earth. They actually go around the whole Earth, around Antarctica. And so they're amazing animals from the point of view of their movement. And these are the animals that were first studied to look at their large-scale movement animals by my collaborators and I. I'm going to give you just a summary of what was found. So this this plot is actually from the original paper. You have, if we look at the time intervals spent outside the water in hours, and you make a histogram of these flight times, then you get this graph. And as you can see, it's a straight line on a log-log plot. And so this is a power law. And in fact, it's an inverse square power law because the exponent, the slope of this straight line is 2 sloping downward. So it's actually -2. The slope is -2. And this suggests an inverse square Lévy walk, that inverse square power law. And Benoit Mandelbrot had looked at this kind of behavior in his famous book on fractals, the fractal geometry of nature, in the context of Lévy dusts. And so this kind of behavior was already known to those who were studying fractals at the time. So let me summarize some important properties of Lévy flights. If you consider power law-tailed step-size distribution, P of L decays as 1 over L to some exponent mu. So for example, if mu is 2, then it's an inverse square power law. And if you look at this power law on a log-log plot, then what happens is if the power law exponent mu is greater than 3, then the standard deviation of this distribution is finite. It's a very easy calculation. So if mu is greater than 3, the central limit theorem is expected to hold, and you should recover Brownian motion in your long time limit. So this is this Brownian regime for mu greater than 3. On the other hand, if you make mu very small, for example, if mu is equal to 1, what happens is you cannot normalize this distribution. It's a non-normalizable distribution. And so you can only take mu going in the limit to 1, but it cannot be equal to 1 because it becomes non-normalizable. In this limit of very low mu, just above 1, so like 1.01, let's say, you essentially have straight line motion because the long steps are dominant and you never make short jumps. Exactly in between these two regimes of straight line motion and Brownian motion, when mu is less than 3 but more than 1, you have the Lévy flight and the Lévy walk regime, because in this interval, the central limit theorem is not applicable. Here are some graphs. So these are plots of position on the vertical versus time on the horizontal for various exponents mu. You can see if mu is more than 3, that's the brown line. You can see that the motion is essentially Brownian motion, and also the jumps are very small. But as you decrease the exponent, for example, if you take mu equal to 2.1, you see these giant dislocations, these giant steps. The position changes almost instantaneously and by a very, very large amount, which is the black curve. You can also see it in the red curve. And these are Lévy flights. On the right-hand panel, you have a very similar type of movement called a Lévy walk. The difference between a Lévy walk and a Lévy flight is that in a Lévy walk, the velocity of the walker is constant. And you can see this constant velocity as the slope of the, for example, this black curve on the right-hand panel. When it is sloping upwards, you're moving with a constant velocity moving forward. When it's sloping downward, you're moving with a constant velocity towards the negative x direction. But otherwise, the behavior is the same. So in a Lévy walk, you have, again, these very large jumps. For example, when mu is small, the jumps are very large. However, the jumps cannot occur instantaneously. They take time. Just like, if you get in a car and you travel very fast, it takes some time for you to go from one city to another city. So that's why the slope of these lines is limited. If you look at the Lévy flight graph, the slope can be diverging. In principle, it can be infinitely large or infinitely negative because there's no restriction on the speed. The jumps are basically instantaneous. Now, obviously, in biology, we're more interested in Lévy walks than Lévy flights. Lévy flights do have some applications in physics. For example, you could look at jumps along a polymer chain. If the polymer chain is folded up, then without violating the theory of special relativity, say a charge carrier or an electron can hop from one point in the polymer to a very far away point along the chain of the polymer. But since it's folded up, the geometric distance is not very large because it's been folded. So Lévy flights do have these kinds of applications, but due to the restriction on the speed, for example, in biology, there's only so fast that an animal can move. You expect Lévy walks to be more realistic than a Lévy flight. And even in other kinds of physical processes, you have upper limits to the velocity, such as the speed of light and so forth. So I will be mostly focusing on Lévy walks for most of this talk, but the mathematical properties of the two are very, very similar, as I will show you in the next few graphs. This plot shows two-dimensional Lévy walks for different power law exponents. You can see for mu equal to 1.5, you essentially have straight line motion. For mu equal to 2.5, you already see something similar to a Brownian motion. And mu equal to 2, which is the inverse square type of Lévy walk, you can see it's neither Brownian motion nor straight line behavior. And it's this type of Lévy walk which is the topic of my main topic of my research. Okay, so I'm going to introduce some jargon, which is the Hurst exponent. Hurst was an engineer, a British engineer working on the River Nile in Egypt, and he was interested in looking at the water levels of the river, and he noticed that if you look at the variability of the water levels of the River Nile, it seemed to depend on the amount of measurement time. In other words, it didn't converge. If you look at the standard deviation or the maximum versus the minimum of the water levels, then if you take a short period of observation, it's different. You get a different answer than if you look at a large period of observation. And this is not how statistical moments are supposed to behave. For example, if you have the average of some quantity and you take a larger sample, you don't expect the average to move very much. Similarly, if you have an average and a standard deviation, you don't expect the standard deviation to change much when you look at a larger sample. But this is what he found, and thus began a big contribution to the study of anomalous diffusion. And in his honor, this exponent called h, which is the Hurst exponent, is defined, inspired by some of his results. So if you look at the mean squared displacement against time, and you put this on a log scale, then we saw that for normal diffusion, because you have linear behavior, the slope should be 1. And the Hurst exponent is defined as 1/2 of the slope. So for normal diffusion, the Hurst exponent is 1/2. For example, for the river Nile, it's not 1/2. It was something else. Hurst actually used a different definition, which I won't be showing here. But essentially, he discovered that the random walk of the water levels did not follow normal diffusion. So here are some other possibilities. So h equals to 1/2 is normal diffusion. H equal to 1 is known as the ballistic limit of super diffusion. This is basically almost straight line behavior at constant velocity. Very rarely, in situations such as turbulent smoke coming from chimneys and so forth, you can have super ballistic regime, super ballistic behavior, which I won't be discussing. When h is equal to 0, you basically have localized behavior or confined behavior. And then you have subdiffusion and superdiffusion. So subdiffusion is when h is less than 1/2, and superdiffusion is when h is greater than 1/2. And both in the situation studied by Hurst in the River Nile, as well as in the movement of animals, it's superdiffusion that is the focus. Now, I had mentioned previously that Lévy walks and Lévy flights are mathematically very similar. I won't go into the technical reasons why their mathematical properties are similar, but here in this graph, these are exact results for the Hurst exponent of Lévy walks and Lévy flights. That dashed curve is a Lévy flight, and the solid curve is a Lévy walk. And you can see that unless you look at very low exponents of mu below 2.0, when mu is above 2, Lévy walks and Lévy flights are very, very similar. And in fact, when the exponent mu is above 3, so you have normal diffusion, the Hurst exponent is exactly the same. Okay. So going back to the animals, so we found these Lévy behavior of albatrosses. Why would they be doing this? And this topic became actually quite controversial, and I'll show you some of the interesting aspects to this controversial debate in a little bit. But in this slide, I wish to present my own personal understanding in as simple a way as possible without using any equations for why animals use Lévy walk in their motion. Why do they move according to Lévy walks? So the top panel shows a computer-generated Brownian walk of 10,000 steps. And on the right, you have the Lévy flight, also with a total distance of 10,000 distance units. But you can see that because of the long jumps, the Lévy flight, it occupies a larger region, so to speak. Now, if you look at the Brownian walk and make a zoom of the Brownian walk, then you get the lower panel. And now you can see why the Lévy flight occupies more space, sort of, geometrically, the hull of the polygon that encloses the Lévy flight is bigger than that for the Brownian walk, and it's because the Brownian walker returns many times to the same place. This returning many times to the same place is known as oversampling in the field, because you're sampling the same point in space more than once. So you're oversampling the same territory many times instead of going and finding virgin territory. So in a nutshell, the reason albatrosses and other animals might be expected to use a Lévy walk, flying or movement strategy is to reduce oversampling so they can find virgin territory where the resources have not yet been exploited. So this is my favorite way to explain Lévy walks and Lévy flights in the context of biology. Let me give you just a taste for some of the other papers that were inspired by some of these results that I showed you with albatrosses and so forth. A large number of other animals have been studied, and similar results have been found for these other animals. So without getting into the details, reindeer, jackals, a type of microorganism known as a dinoflagellate, spider monkeys in the Yucatan Peninsula, sharks, and I will come back to sharks in a little bit, fruit flies, honeybees, and so coming back to sharks, as I had mentioned, this issue of the Lévy walk movement became quite controversial for a number of reasons. I mean, it wasn't just the mathematics; it was also the empirical side. Whether experiments were done properly and so on. And it was only in 2008, and then in 2010, that two papers published in Nature more or less settled the matter. So the group by David Sims, they looked at millions of data points, and not just of one species, but of several species. So they looked at sharks, bony fish, sea turtles, and penguins. And they used statistical inference using Akaike weights and so forth, and were able to more or less convince the community that Lévy walks do really happen. So that at least on the biological side of the debate, the question is more or less settled. Finally, in 2019, just before the pandemic, the same group of David Sims, they came up with a very, very interesting and quite surprising result, which even led to an article in Quanta magazine. And what they did was the following: they took some larvae and destroyed. They blocked the sensory mechanisms of the larva so that the larvae were moving, so to speak, blindly. They use a sensory blockade using I think it was a genetically engineered organism, and they could use light to turn on and off the sensory mechanism. And what they found was quite unexpected and surprising. They found that when you block the sensory apparatus, the larvae seem to move closer to a Lévy walk than when their sensory apparatus is working. And of course, this is exactly what you would expect if Darwinian natural selection had led to mechanisms, neurophysiological mechanisms for generating Lévy walk type of behavior. So this is more or less the situation on the biological side of things. Let me talk a little bit of humans. Human movement has also been studying, and there are very interesting results about how humans move. Rather than go into the details of these studies of human movement, because modern human movement has many factors. For example, we move by car, bicycle, we take airplanes, and some of the ways that we move are constrained by the transportation networks and so forth. For example, when I have to go, say, to the country where I was born, which is India, there's no easy way for me to go from Natal, where I live, to India without first going to Sao Paulo. So I actually have to fly south and then back north. So there are these complicating factors. But let me show you these this interesting bit of a history of human colonization, which is not which happened before the industrial age, and the only transportation technology they had were boats and ships and so forth. So in when linguists started looking at the languages in Africa, they were surprised that in the island of Madagascar, they found a language that was not related to the languages of continental Africa, and was instead more closely related to the languages spoken in Southeast Asia. So this was a big surprise. And so just a quick summary. Languages are classified in families. So for example, Portuguese and English, they are Indo-European languages. Latin and Greek, Farsi, Hindi, these are all Indo-European languages. But there are languages which are not, don't belong to this family. Now, for example, the Basque people, the language of the Basque people is not, doesn't belong to this family. Arabic, Hebrew, Aramaic, they belong to a different family, a different language family. My own native tongue, which is called Tamil, is also a non-Indo-European language. It's called the Dravidian family. And so these, the idea of these families of languages is very a useful way to look at the relationships between languages. Often it's because they have a common ancestor. So for example, say Portuguese and Spanish are descended from a common ancestor. So this is the idea of the language families. Now, there is one of the most widely distributed language families is called the Austronesian language family. And this map shows the extent of this language family. So it is spoken in Indonesia, in Madagascar, parts of Polynesia. And I think there are small numbers of people who speak it in places like Taiwan and in East Asia. But as you can see, it's a huge extent. It's more than, I mean, if you look at it from in terms of the longitude, it's more than half the Earth. It's quite spectacular. So the question is, you know, how did the languages spread? And the usual theory of how languages spread is simply that people go and colonize the neighboring territory, and then from there they keep going to the next nearest neighbor location and so forth, like a wavefront propagation. And this is indeed probably how human colonization proceeded for the most part, little by little, step by step, you know, kilometer by kilometer. However, in the case of the Austronesian language that came to Madagascar, there's a big problem, and that is thousands of kilometers separate Madagascar and the nearby islands, which I'll show you on a map in a little bit. Thousands of kilometers separate Madagascar from Indonesia, or in fact, the closest other point where these languages are spoken. And there is no intermediate part of the world where these languages are spoken. For example, if you look at the map, you can see Sri Lanka is sort of somewhere in between. If you go slightly to the north, you can say that Sri Lanka is sort of halfway in between. But the language never reached Sri Lanka. There's no historical evidence that this language was ever spoken in Sri Lanka, even by small pockets of people. And so the question is, how did this language reach Madagascar? And the answer is, you just can't explain this via the conventional way of thinking of human colonization, which is Brownian motion, Brownian diffusion. So if you look at if you implement Brownian diffusion in population growth models or any other type of model to see how some feature or virus or organism, or in this case a language, how it would spread, you would have wavefront propagation. So if Indonesia sent out a wave of speakers of this language, and they reached Madagascar, as you can see from this figure, they should have reached continental Africa at the same time, or maybe here in the northeastern corner of Africa, maybe even before reaching Madagascar. But there was absolutely no historical evidence of any kind that these languages reached continental Africa at all, except from Madagascar. On the other hand, if we entertain ourselves with the possibility that maybe even human colonization, even human diffusion, has elements of Lévy flights or Lévy walks, then you can have a single event, just one ship, just one boat, or maybe a shipwrecked family. You would only need, in principle, one man and one woman to be able to carry this language and repopulate and populate, generate a community, father a community of people who speak this language. Most likely it was more than just two people. But the point is, maybe it was a single event, you know, the sort of black swan event, or the single but large event that changes history. And today we have Madagascar, an island that speaks Malagasy, which is belongs to this language. Let me show you some more. Let me make this argument a little more precise. So this is Madagascar, and you have these islands around it: Comoros, Mauritius, Reunion, Seychelles. And if you look at this figure, you can see that if the colonization did not occur according to a Lévy type of behavior, but rather Brownian diffusion, then as soon as Madagascar received the language, then these other islands should also have received the same language. In fact, these other islands did not acquire speakers of this language family until much, much later. So once again, we see that it was a single event. It was not a wavefront type of event. It was a single event. And so to go back to this figure, even human colonization and spreading may be governed by some of these exotic type of movements. And here it's worthwhile reflecting again on the issue of free will, because we think humans are governed by free will, but clearly on a statistical level, that's not the case. It looks like humans are, at least our macroscopic behavior, follows more or less statistical patterns. Okay, so let me see how much time I have. Okay.
Randy, yeah, you have another half an hour?
Okay, very good.
Great.
Okay, so what I would like to do now is show you how, what is the mathematics for why Lévy walks and flights can be optimal for searches. And then I will show you some details about that led to the controversy. So after the albatross results came out, and we really wanted to understand what was going on, we needed a very, very simple mathematical model for how the animals move, so that we can start running simulations to try to understand what's happening. So we made the following very simple model of animal movement. It's a very simple model in the sense that it neglects learning, and it neglects nervous systems and other details, but it should capture the statistical aspects which dominate the long-term behavior. So the movement is as follows. If the animal, okay, first of all, the animal has a radius of vision, a radius of detection. In this figure, I've labeled it RV, radius of vision. If there's a target inside the radius of vision, then the animal moves straight to the target of vision. So on the left panel, you have the circle, which is the radius of vision, and the black square is the target. It can be the food, or it can be whatever the animal is looking for. Since it is inside the radius of detection, the animal moves straight to the target. On the other hand, let's say there's no target inside the circle. Then the animal picks a random direction and a random distance, and we impose the power law of distribution, because that's what we are studying. And then using this random distance and random angle, the animal moves incrementally looking for a target until one is found. If nothing is found, then you pick a new distance and a new orientation. So on this panel B, you can see the little, now the circle is small because we're zooming out. There's no target inside it. So the animal picks a straight distance sort of sloping downwards in this figure and goes looking for the target. There's nothing found, so then it makes a new direction and a new distance. And it keeps doing this zigzag behavior until eventually a target will come inside the circle, inside the radius of detection, and you will be able to eat or consume the target in some way. Now, the great thing about this model is that it is so simple that you can get a good, you can get reasonably good results, a good approximate results for this model by using a technique which is very widely used in physics called the mean field approach or the mean field approximation. And the essential idea behind the mean field approximation is that you neglect fluctuations and you only look at mean quantities. This was very widely used in the beginning of the 20th century to study magnetism and other kinds of phenomena with phase transitions. But without going into details, let me just say that this model over here can be solved, and the results are the following. If, when the animal finds the target disappears and it dies, but somehow we keep the global target concentration fixed by, let's say, new targets are born somewhere else to keep the target density constant. In this situation, the optimum search strategy, the optimum value of mu, the power law exponent mu, suggests ballistic motion. In other words, you just go in a straight line, never turn back, just go straight, 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 and you will find the target, and then pick another direction and angle, go straight, 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 never turn back. This is the optimum solution. But let's say that the target, after the animal finds the target, it can recover. And this is a very common scenario. For example, let's say that an insect goes to a plant where there are flowers. It feeds on the flower and consumes all that can be consumed. So now there's no more nectar or whatever. But maybe the next day, the plant will have new resources. And so the insect can come back to the same plant after some time. So if you allow a return to the previously visited location after some time, then it turns out that the optimum search strategy converges to an inverse square power law as the target density becomes very small. The optimum mu, which I've shown in red, is 2 minus a correction delta, which goes to 0 in the limit of 0 target density. In other words, when there's very, very little targets, then you have a condition of scarcity. And in this situation, an inverse square distribution is the optimum value of the exponent mu. This plot is actually taken from the original paper. You can see that the simulations and the analytical results are strikingly similar. The only difference is for simulations, you cannot simulate when mu is 1, since it's non-normalizable. And so we concluded, sort of boldly concluded, that inverse square Lévy walks are optimal in one dimension, and we went on to think that this was true also in other dimensions. Now, like I said, this calculation is called a mean field type of calculation because it neglects fluctuations. So technically, it's not correct. But in a few years after our original results, we published mathematically more sophisticated solution. And it indeed it's mathematically messy. We have to use a type of operator known as an integral operator, and you have to interpret the results carefully and so on. But the important point is that this result that we got using the simple mean field approach, which is only approximate, we were able to put on a very firm footing, a mathematically rigorous footing. So in one dimension, the problem was solved. And we believed that the same should hold true in 2 dimensions, in 3 dimensions, and so on. And our argument, I'd like to summarize our thinking for why this should be true in every dimension. And it has to do with the Hurst of exponents. So when if you have a Lévy index less than 1, and this is the same as saying mu less than 2. So if you have a power law that is more fat than the inverse square power law, then the Hurst exponent is 1. This I showed a graph of the Hurst exponent versus mu some time ago. In fact, let me just quickly go back and show you here. So if mu is less than 2 over here, the Hurst exponent of a Lévy walk saturates at 1. It can't be more than 1. But on the other hand, for alpha greater than 1, or in other words, for mu greater than 2, the Hurst exponent decreases. And so you expect that the best of both worlds is when alpha is exactly 1, which corresponds to mu equal to 2, or the inverse square Lévy was. So now this is sort of a hand-waving sort of argument. It's not precise. But often when we deal with high-level concepts such as Hurst exponents and so on, even though the result isn't rigorous, you expect that because these concepts are deep, that there must be some validity to these kinds of arguments. And we were very confident in this argument, and so we claimed that inverse square Lévy walks, which corresponds to Lévy index alpha equal to 1, is optimal in any dimension. And we have claimed this in many, many papers, and we never questioned it. However, very recently, just before the pandemic, a paper directly contradicted this claim, and this surprised us because we were very confident in our argument. But like I said previously, only the one-dimensional case was established in a very rigorous way using the integral operator methods for 2 dimensions, for 3 dimensions, and so forth. To this day, there are no rigorous mathematical results for the optimality. It's still actually an open problem, and in fact, maybe some of you who are mathematically inclined may become interested in this problem, because it will be a big achievement to show to resolve this issue in a mathematically rigorous way. So to this day, it's still open. Now, as far as physicists are concerned, however, the controversy has more or less died down. I will show you why. But I just wanted to try to convey to you how even we were surprised, because the argument of the Hurst exponent is a very powerful and reliable argument, and yet it's not rigorous. And so maybe it was wrong. So, we needed to find out what was happening. So many of my collaborators and I, we became newly interested. And it was very interesting because it was as if we were going back 20 years and starting everything from scratch. It was quite an interesting experience. So here is the paper. Let me see if I can take it out of the. Let me make this slightly smaller so you can see. So this is a top physics journal called Physical Review Letters, PRL. And this paper was published in 2020. And you can see just from the title just how controversial, how much controversy the paper stirred up. So it's a direct contradiction of the claims of my collaborators and I that we had maintained for more than 20 years. So the title of their paper is Inverse Square Lévy Walks Are Not Optimal Search Strategies for D greater than equal to 2. Now this is very important because in D equal to 1, like I said, the results are rigorous. So it's only for D greater than or equal to 2 that these authors were questioning our ideas. So I will try to hurry here because of the time. This paper made 3 claims, which I have summarized here. The first claim is that the capture rate, eta, and the capture rate is the same as what I call the search efficiency. So that is, how many targets do you find in a certain amount of time? So the capture rate has linear dependence on the target density rho for all values of the Lévy index alpha. Claim 1, we agree with. So it's not controversial. Claim 2, the gain, this is the relative gain. So it's eta max, the maximum efficiency divided by the efficiency, achieved by varying the Lévy index alpha, which is the same as varying the power law exponent, is bounded even in the limit of 0 target density, so that tuning the power law can only yield a marginal gain. So claim 2 directly contradicts what we were saying. And claim 3, depending on the values of the radius of detection A, the restarting distance, and the scale parameter, the optimum is realized for a range of alpha. Claim 3 is also not controversial because it was well known. It has been well known for more than a decade. So I'm going to focus only on claim 2, which is the idea that the mu equal to 2 can only yield a marginal gain. So, okay, let me take this out of. Okay, so there are in general 2 relevant length scales in this problem. So I have drawn here the searcher at the center of this circle, and there is the distance LC, which is called the restarting position or distance. That is, given the position of the target that you previously found, how far away from the previously found target do you restart your search? So that's this distance LC. A in this figure is the radius of vision, which is what in a previous slide I called RV. But these authors preferred to use A, so I decided to stick with their notation. So there are 2 important length scales. The first length scale is LC divided by A. So that's the restarting distance in units of the radius of vision. And then you have another length scale, which is the distance between the 2 targets in units of the radius of vision. So you can see there's a second circle, which is the other target. And the distance between the centers of these circles is the restarting distance. Sorry, is the separation distance. So these are the two length scales. Now, in one dimension, what happens is that this distance that I've marked in blue is invisible to the searcher, because as soon as he comes to the edge of the radius of detection, he finds the target. There's no way to sample this part of the interval that is in blue. However, in 2 dimensions, this is not the case, because in 2 dimensions you can go around the target. Let me show you here. So as you can see, let's say you have these 2 red dots correspond to 2 different restarting positions. And as you can see, the path of the searcher can take you to the other side of the target, but without finding the target. And so both length scales are important in 2 dimensions, but it's not important in 1 dimension. Now, in the PRL paper of 2020 about saying that the Lévy walks are not optimal in dimensions greater than 2, the PRL authors kept one of the length scales constant while taking the limit of 0 target density. The length scale they kept constant is the restarting distance divided by A, but this figure shows how the restarting distance is important in 2 dimensions. You see, for example, the red dot that is closer to the blue circle, it has a smaller chance of being able to go around the target, because even a small step to the left and it will find the target. So it's not going to be able to go around. But this farther away target has a greater chance of being able to go around or somehow missing the target. And so this ends up being an important what happened here? Let me just remove this. What's happening? Just one moment. I'm not able to remove this. Yeah, I will just keep it like this for now and go like this. Let me see what.
Randy, it's X on the upper right. Just click X. There is to close it.
Yeah.
Yeah.
If I do that, will I not close the presentation?
Is this?
This one?
No. Okay. Yeah, it's fine. I'm too confused. What the hell is happening? It's fine. You can continue. Don't worry.
What did I? One moment. Let me see what I did.
Theoretical physics.
Okay. Good.
Very good.
All right. Sorry about that. I'm almost finished. Okay. So, to summarize, what happens is if you keep one of the length scales fixed, then you're not really looking at the full space of the possibilities. In particular, if you look at this figure, the key point is that the second length scale is related to the curvature of this blue circle. Now, for example, let's take the Earth. If you look at the Earth from the moon, it looks spherical or round. But if you look at the Earth from where we live, the Earth looks flat. And so this is what is happening. If the curvature becomes imperceptible, then of the 2 length scales, only one remains visible or relevant, and the other length scale is not in play. So you should expect a recovery to the 1D behavior. This is sort of like the flat Earth behavior when one of the two length scales goes to the minimum value. And let me just show you the results here. Okay, so these are some results. There are many parameters here, like sigma, rho, and delta. Don't worry about this. The important thing is that, as you can see, on the vertical axis, you have the search efficiency, and it can be made to go arbitrarily large. In fact, here is the mathematical expression. And this shows that the search efficiency are not marginal even in 2 dimensions. So we were very pleased when we found these results, because we were worried that maybe the Hurst exponent idea was wrong, but these results showed us that that was not the case. What had happened was that the authors of the PRL paper had kept one of the length scales fixed. Let me quickly show you. Let me just show you that these ideas we were able to put on a slightly more firmer footing. Like I said, the mathematically rigorous treatment of the problem is still considered an open problem. But as physicists who work with the numerical simulations, we were able to show, using models of Lévy walkers inside spherical shells and inside annuli, which can approximate this problem like a proxy. It's a proxy problem for the Lévy walk search problem. We were able to show that inverse square Lévy walks are optimal and can lead to arbitrarily large gains in efficiency in 2 dimensions as well as in 3 dimensions, as you can see in these black curves, which is from this paper that we published 2022. So due to time, let me end.
Okay.
Okay, so let me just 1 minute for
Sure,
some of
1
these
minute.
topics.
Sure, 1 minute. Just 1 minute.
First point is that the empirical side of things was much messier than I have shown you. And second point is, it turns out Lévy walks are optimal even in situations we didn't expect. This is the book that Ahmed mentioned previously. And let me end by saying, okay, so yeah, let me end. So we saw the behavior of maybe even human behavior has elements of this kind of exotic behavior. And there's much to study in this type of regime, which is neither fully random nor fully deterministic. In the case of Lévy walks, the statistical laws evolve, the probability density function evolves deterministically, but not the trajectory. So I think I will end here. Thank you very much.
Thank you, Randy, very much. So, of course. Okay.
Thank you, Gandhi, for the lecture. Here, Emmanuel, nice to see you again. My question is about your exponent mu equal 2. You have mentioned there's evidence in nature about this exponent, but in macroscopic level, when cell movement, bacteria, something like that, you have this evidence, or just in macroscopic level in animal behavior movement? This is my question.
A very good question. The study that comes to mind that I remember is the study of dinoflagellates. They're not bacteria, but they're a microorganism. Now, the general rule is no animal is going to move in Lévy flights if the targets are nearby. Only if the targets are very far is there any reason to fly very far or to move very far. So even with bacteria or these dinoflagellates, we expect that if there's a lot of nutrients or if there's a lot of food, they won't lose. It's only in conditions of scarcity.
Hi.
Did I answer your question? Did I answer your question?
Yeah, yeah.
Yes, yes.
Hi, I have two questions. The first one is if our visual system, like our eye movement, follows these Lévy walks or not.
Excellent question. And these eye tracker data were studied by several groups. One of them is the group of Theo Geisel, and the book, the Physics of Foraging book, it discusses some of these results. It's very similar to a Lévy walk, but the exponent is not. The exponent is higher, and so technically, I think it's not a Lévy walk, but it has many features in common. I haven't had time to study these types of data, but there's certainly some kind of power law type of behavior there, but I don't think it's the exponent is 2. It's greater than 2.
Okay, thank you. And the second question is, if I understand correctly, Lévy walks, you have each step is independent, right?
Yes, yes.
So animals have memory and they can smell and they can tell whether they have been in a particular place before, right? So is this important in this problem or is not? Yeah, that's the question, I mean.
Yeah, very interesting. Let me show you some graphs I didn't have time to discuss. So for example, here, you see these real animal trajectories look more like this, and they don't look like straight lines that have been joined together. So the mathematical Lévy walks looks like straight lines, and then straight lines, and again straight lines. That's not how animals move. Now what happens is, let's say the animal has some memory. For example, let's say it has some memory of some food or some other thing very far away. It might move towards that place, but not exactly in a straight line. So it might go slightly to the left and slightly to the right, but maintaining the overall direction. For example, let's say it's north, so you'll go a little bit east, a little bit west, but maintaining the north heading until you reach that location. So this will look like the steps are not independent, you see, because the direction is slightly changing. But you could also model it as a single jump, a single large jump. Instead of many small jumps, you could model it as a single large jump. The correct way to treat this type of situation is using the tools of renormalization group theory. So you take the random walk and you look at how it renormalizes, and then you get a better feeling of what the animal is really doing. This is a very good question you ask, because the same exact trajectory, if you look at different sampling frequencies, so for example, you can sample it, let's say every 1 centimeter, or you could sample it every meter, and you get different kinds of ideas of what the animal is doing depending on how you look at the sampling resolution. But when you look at it in terms of how the movement renormalizes, you get a different idea of what is happening.
Hello, Gandhi. Thank you for your talk. I was thinking, how do you generate these rewards? Like, how it's distributed? Because I think this can impact a lot what's the optimal exploration strategy.
Yeah, I understand. So you mean, for example, each target has a different reward, right? Is that what you mean?
Just how do you simulate an environment with some targets, or it's one target at a time, if I understood. But if you simulate an environment with more rewards, how this can impact? Because in the natural environment, this is the situation. You have food in all sort of places, and the animal has to explore, but well, finding food, it's not just one specific food is going to be good.
Yeah, so very good question. So usually you have to put many rewards. So in the very first studies, the idea was you only have one type of reward. They're identical rewards, but you only have one type of reward. So each target gives a reward, but it's exactly the same. Then people started looking at what happens if you group the targets together. For example, you don't make it uniform, homogeneous. You make it heterogeneous. You make the distribution heterogeneous. So now there'll be some regions with more rewards than other regions. So what happens in this situation? And then people also started looking at when you have not only heterogeneous rewards, but also different types of rewards. So for example, a small reward and a big reward. What happens? And these kinds of problems have been studied. I don't remember all of the papers. But what is fascinating is that some features, unexpected things happen. So for example, we've started seeing that if you have heterogeneous grouping of rewards and targets, if you have patches of reward, patches of targets, what happens when you apply renormalization group ideas to a patch? If you start zooming out, then what happens is one patch of many targets can be thought of as just one target. And so at the macroscopic level, you see the same type of dynamics emerge as you had for just one homogeneous type of uniformly distributed target. But it's a very interesting question. I don't know, I don't remember everything, all the literature, but a lot has been studied and it's very interesting. So it's a good question.
Great. Yeah, in the interest of time, thank you, Gandhi, very much for this exciting talk. And yeah, hopefully next time in person. Great. Take care. Bye,
Thank you
Gandhi.
very much.
Bye-bye. Bye-bye.
Bye.
Okay, so now we'll have a break, and the tutorial will be at 11 with Albin and the computer lab, okay? Thank you, Gandhi. Good.